good afternoon, good morning, good evening, everybody. So thank you very much to join us today for the talk that will be done by Professor Sachin Sapatnekar. So then I give the floor to Graciele to do the presentation of Sachin.
Thank you. So thank you, Hayes. Thank you for this invitation. Actually, it's a huge pleasure to be presenting Professor Sachin here. So Professor Sachin was my co-advisor, and he helped me a lot during my PhD and even after. So it's since 2013 we worked together. And it's a very nice. Now I have some students from him working in the same thing, and also some students, like, for example, from Professor Janhu, that was advised by him, that just joined my team. So it's a big community, like, and we are all together. So it's a huge pleasure. So Professor Sachin is the Henley Chair in ECE and distinguished McKnight University professor at University of Minnesota, and serves as PI of the Align projects. His current research interests include design automation methods for analog and digital circuits, circuit reliability, and algorithms and architectures for machine learning. He is a recipient of the NSF Career Award, the SRC Technical Excellence Award, the Semiconductor Industry Association's University Researcher Award, and he has 2 Best Paper Awards. He has served as editor-in-chief of IEEE transactions on CAD and general chair for the ACM IEEE Design Automation Conference, DAC. So he's a fellow of IEEE and ACM. So I could talk many other things. So Professor Sachin is very recognized in the industry, so respected, and everybody says, oh, if it's a student from Professor Sachin, I'm pretty sure he's a very good student. So it's a pleasure to have you here. Thank you, Professor Sachin.
Thank you, Graciele. Thank you, Ricardo, for inviting me. It's a pleasure to be here. So today, I'm going to be talking about a new research direction that we've been following in my group for the last couple or 3 years. And we've been looking at automating layout for analog circuits. Now, this is a problem that has been around for a long time, maybe about 30 years or so. People have been working on it, but there hasn't really been much of a dent in the problem. There hasn't been much widespread adoption in industry. And we are trying to change that. Now, there are several factors why I think this time is different, and I'm going to talk about them, and I'm going to give an overview of our approach. So the project that we are working on is called Align, which is a joint project between 2 universities, University of Minnesota, Texas A&M University, and Intel Labs. So in fact, one of the things that's different this time is that there's such close cooperation between universities and industries, bringing sort of the best of both worlds over here. I'm going to start by motivating the problem. So first of all, what's important about analog circuits? Today, to a greater extent than ever before, analog circuits are omnipresent. So they are part of any interaction between a computational engine and the real world, because the real world is inherently analog. Now, this becomes kind of much more important because the old paradigm for computing was that you had kind of really strict number crunching type of computing. But today, computing is cell phones, it's IoT devices, it's robots, it's all of these things. So this has actually changed a lot. So if you look at wireless infrastructure, for example, that's really a key component of any kind of distributed computing engine. So all of that is really RF communications. If you look at data centers that are shown over here, that again is a really important analog application, because you have high-speed I/O circuits that are inherently analog in nature. In addition, there are IoT-like applications such as smart cities or smart grids, or you have autonomous vehicles that have to sense the environment. And you can see why analog is becoming much more important. Core processing is still largely done in the digital domain, but the interface with the real world is really pretty strongly analog. Now, for a lot of these applications, the specifications on analog circuits are very stringent, but for some of them, they're kind of not that stringent. You just need to sort of get the job done. And this is the low-hanging fruit for automation. So our goal is really to kind of enter these lower performance applications, but also make a dent in higher performance applications. You should notice also that even when you talk about so-called digital systems, this is a teardown of an iPhone 12 from iFixit.com. Even when you look at these, there's actually quite a bit of analog in here. So these core chips, the SoC, the DRAM, the flash memory are fundamentally digital-like chips, if you call memory digital. But if you look at all of these, the communications chips, the power delivery chips, power management chips, the accelerometers and sensors, those are basically analog-like chips. So even in so-called digital systems, there's quite a lot of analog. If you look at even an older 45 nanometer CPU, there's quite a bit of analog in here. For example, if you look at the I/O circuits over here, these are fundamentally all analog-like circuits. Within the circuit, you also have PLLs, which are used to generate clocks. You have sensors, which are used to test for temperatures, etc. And so you can see that there's actually a pretty strong component of analog, even in so-called digital systems. Now, why is this important? It's because when you design a mixed signal chip with partly digital and partly analog components, really analog design is often the bottleneck because it's very human intensive. So if you look at the relative proportion of digital versus analog components on a chip, by area, digital dominates massively. But by design effort, you can see that analog actually has a very strong contribution. And so if we could reduce this design effort, we would be able to accelerate time to market, and we would be able to allow for better overall design. The other reason for doing this is it's not just about the area, but it's also about the fact that the design risk is increased when you perform analog design. If you look at a large number of respin issues of post-silicon failures, they are related to the AMS or analog mixed signal part of a chip. And so if we can automate things and make them correct by construction and even provide enablement to the designer to help them perform the design iterations in a better way, then that would be a really important step. Now, if you think about how analog design proceeds, analog designers are fundamentally artists. They have a lot of intuition. They're very skilled. Unfortunately, they're also in very short supply because it's such a strong skill. So our goal is really to try and enable people who are experts in analog design to take care of some of the parts that automation is well equipped to perform. So over here, you can see a back of the envelope picture of amplifier drawn on a napkin, and then that needs to be translated to something like this. So the circuit designer would typically look at the circuit at the transistor level. So they would take, say, a SPICE netlist, they would optimize it, or they would optimize the topology of the amplifier and perform some kind of circuit level optimization. And then after that, they typically hand it off to a layout engineer. And the layout engineer is typically not kind of conventional engineer. They really are very good at placing rectangles and trying to build the chip according to the specifications. So in this case, the thing is that if you look at the performance of the circuit, really depends very strongly on the parasitics. And the parasitics depend very strongly on what the layout engineer does. So the circuit designer, because they're working independently of the layout, they have to make their best guess at the parasitics, which may or may not be correct. And so if you can have a tight coupling between these, that would be really beneficial. As you can see over here, this is really the way that you proceed. You have quite a few iterations that are required to get it right. So you go through some kind of a high-level architectural design, cell layout, system layout, and you go this way, and then you may have to kind of loop over this multiple times to get it right to meet specifications. So this is a sort of a cartoon picture of how you perform this netlist design versus layout design. So at the netlist design level, as I said, the circuit designer may perform circuit transistor sizing, topology selection, etc. And then they hand it over to the layout designer who performs manual layout, placing these rectangles. They generate individual cells. They perform placement and routing. And all of this is manual because unlike digital, there are a number of constraints that are traditionally hard for the layout tool or automated tools to handle. So as a result, this is a time-consuming, manual-intensive approach, which often takes days or weeks. So when this is done, that's when you have a true picture of the parasitics, and that's when you know whether the optimizations you made at this stage were good optimizations or not. So you come back with these parasitics and then say, well, okay, maybe I should re-optimize. And this is going to be a shorter time cycle than this because hopefully an experienced designer gets the big picture right here and needs to perform some tuning over here. But then again, it needs to go through layout, and that again takes several weeks. And this fundamentally acts as a bottleneck on the speed of the design cycle. Now, if we could take this green box and if we could kind of make it much faster, then this would actually help a great deal. Because if we could do it automatically, and if we could do this within hours instead of days or weeks, then we could actually speed this up and we could perform the next optimization cycle here. And since this has been sped up, you can actually perform other optimization cycles, and you can actually end up getting a better quality layout because of this. So the goal of our project, which is called Align, it stands for Analog Layout Intelligently Generated from Netlists, is to create efficient, automated, high-quality layouts. And this will help in both in terms of turnaround time and also in terms of design quality. Now, we are not the first people to try to do this. There's a quick history that's shown over here. In about the 1980s or so, there were initial efforts which were kind of procedure-based or rule-based and so on. This gave way to optimization-based frameworks in the 1990s. And then even since then, there are a number of groups that are active in this area. Several of them are listed over here. And we're really kind of standing on the shoulders of all of this effort, leveraging all of the good work that they've done and trying to kind of take it beyond this. So now the question is, what's different this time? Why would we expect to be any different from all of these efforts? And I'll point out a few factors that have changed now. The first of these is that we are now in the FinFET regime. And so this means that a lot of analog design is being done at, say, 16, 14 nanometers or 10 nanometers or 7 nanometers. Not because this is kind of the analog designer's desire. An analog designer would prefer to work in an older node, which has lower variation and so on. But because chips have to be integrated with both digital and analog parts together, it's inherently required that the analog part must be close to the digital part, and that pulls it down to lower technology nodes. In these FinFET technologies, there are very restricted design rules. So for instance, you're limited in terms of the directionality of wires. You cannot have arbitrary zigzag wires on the same layer, especially because of coloring rules and so on. And so your layouts actually look very, very regular. This is much more different from how they used to look in the past. In the past, an analog designer or a layout engineer could actually be a real artist, and they could enforce requirements such as symmetry by creating zigzag routes that were really hard for an automation tool to emulate. And so this kind of freedom from choice actually restricts the design space and makes it more it's more easy for a design tool. Moreover, some of these design rules are actually hard for even the layout engineer to understand, but they can actually be encoded as Boolean rules for a layout tool. So that's actually a benefit, an advantage for an automated tool. The other issue here is that if you look at previous approaches, they've largely addressed one type of or one class of analog circuit at a time. Analog circuits are very diverse. So broadly, we've divided them into 4 categories: low frequency analog circuits, such as say low frequency data converters, amplifiers, etc. Wireline circuits, which are high speed link circuits for data communication, IO, etc. Wireless circuits, which are RF circuits, and power delivery circuits, such as voltage regulators. Now, for each of these, the kinds of constraints that are important are different. So on the y-axis, you'll see the classes of circuits. On the x-axis, you'll see the types of constraints that we need to worry about. Low-frequency analog circuits, for example, worry a great deal about matching active and passive devices, transistors and resistors, capacitors, etc. But that's much less of an issue for power delivery circuits, where matching is not that important. Some of these circuits require you to consider inductors, but not others, etc. So the considerations are very different. And what we are trying to do over here is to create a universal framework that can work for across a wide range of circuit types. The third thing that has changed is the advent of machine learning. So in the past few years, machine learning really has made rapid strides, and we've been able to do a lot of things that we were not able to do earlier. Fundamentally, machine learning is very good at capturing things that are, for example, rules or techniques, etc. And in some sense, it actually emulates the experience of the human designer if you provide it with enough training. Now, machine learning is often exaggerated. I don't want to claim that it's going to solve the entire problem, but if you can leverage it in an appropriate way, then we can make quite significant advantages. But it's still pretty hard because if you look at, for example, FinFET technologies, the parasitics really dominate. So there's an increasing gap between schematics and post-layout simulation and silicon because of this. There are much more complicated and restricted design rules. For example, if you look at VR rules, there might be some kind of a Boolean relationship that says that I'm allowed this configuration of VRs, but not this other configuration. And it's not as simple as distance between VRs. If I look at the structure of the transistors, we're looking at FinFETs, which means that self-heating really becomes a big problem that leads to reliability issues. And in both devices and interconnects, we have to be very aware of these reliability issues. Okay. So the overall approach in Align looks something like this. Our input is a netlist, and the netlist may not have any annotation. It may just be a SPICE netlist, so we need to kind of detect the hierarchies in that netlist. Our output is a layout in the form of GDS. So if I have a netlist of this sort, the first thing I need to do is to recognize the components of that netlist, which would be, for instance, a circuit schematic of this sort. We start over here. In case we do have the schematic, we can actually use that information. But in the most general form, we'll start from here and recognize the components over here. Now, when you recognize this, it's not just about recognizing the blocks. It's also about recognizing lines of symmetry. So over here, for instance, you can see there's a line of symmetry that's horizontal so that the top and the bottom half should be reflected across each other. And this becomes really important for avoiding process-induced mismatch in analog circuits. Once you have this, we generate the auto annotation. We also detect lines of symmetry, any kind of matching requirements, and so on. Next, we look at the specs, and from the specs, we try to generate constraints on the electrical performance. So for instance, if some parasitics are really important, then we try to make sure that those parasitics are limited. All of this is purely at the level of the netlist. At some point, if you're going to generate layout, we need to think about the design rules and the specific process technology. And this is where this part comes in. So the process design kit, which contains the technology rules, are abstracted in a form that I'll talk about later. And then once you abstract this, and once you have the hierarchies and the requirements, now you can start generating layout. So we start with these hierarchies. We generate layout for the smallest level blocks, and then we perform block assembly at multiple levels and hierarchically build the solution that looks something like this. So in this case, for instance, we might take a circuit and generate a layout that looks something like this. In various parts of this, we use machine learning models to assist the process. As I said, this is not a singular effort. This is the effort of a large team. These are some of the people who are currently working on this. There are others who've graduated since then. This is actually supported by DARPA, and it's a fairly major project. We are also working with some other people outside the team who are users of our tools. So let me kind of talk about how we identify these hierarchies and how the overall flow works. I'm going to use the example of the switched capacitor filter again. It has an amplifier here, it has switches, it has capacitors, and this is the overall structure. And like I said, there's a line of symmetry going through the middle. So remember that this is really provided to us in the form of a SPICE netlist. We don't have the schematic view. So the first thing we want to do is to actually recognize that there are these building blocks over here. So for instance, we might want to recognize that there's an operational transconductance amplifier as shown over here. And this OTA or op-amp can be kind of extracted from here. And the op-amp internally consists of a netlist of these types of transistors. Then we can go to a next level of hierarchy. We can say, well, these actually have various types of building blocks. For example, this is a differential pair, this is a current mirror, this is a load. And so we can come up with these. And when we come down to the smallest level, then we have just a few transistors in each of these. Now, in FinFET technologies, this may actually be multiple fins or multiple parallel transistors, etc. But the basic idea is in the schematic, they're just really a small number of transistors. At this point, we can start assembling the layout because these are very known and specific structures. So if we can generate the layout for this, we first need to take considerations from the process design kit. And we use a kind of a gridding scheme that I'll talk about in a little while to abstract these design rules. Based on this, we have templates for building the layout of each of these primitives. So based on these templates, we can build the layout of these primitives. The primitives can be parameterized. So the W by L can be some variable value that depends on the specific design. So for the specific value in this netlist, we can build the layout for these. So this shows the layout for differential pair. It shows two possibilities. The first one is what's known as the common centroid structure, where the centroid of the A transistors and the B transistors is over here. The other is the interdigitated form, where A and B are interleaved, and each of them has various advantages and disadvantages. And so depending on your performance requirements, you might choose one or the other. Once you have these structures, you can go to the next level, and then you can build the layout of the OTA. And this is really just a matter of taking all of these, using some place and route scheme to construct this. Now we go to the next level block where we have the layout of this block. We have layouts for the capacitors and the switches, which are also primitive structures. They are basic structures that are used. And we get the final structure that looks like this. The OTA now is really a small part of the whole structure. It's this thing turned by 90 degrees over here. You have the capacitors, which are stored, which are represented as arrays, and those are these structures here, and the switches are over here, and that's the final layout. So the overall philosophy is extract the hierarchies, build the primitives, and then start building the layout block by block, keeping in mind the constraints that are required, such as symmetry constraints or performance constraints. So I'll talk about each of these pieces one by one. Let's first talk about taking the netlist and annotating it to figure out what the building blocks are. Now here, there is a fundamental problem, because when you look at the structure of an OTA, if you're provided that in terms of a netlist or even a schematic, it's relatively easier for a human designer to look at this picture and instantly say that it's an OTA. For a computer, it's not that easy, and the reason is not because of this specific OTA, but because this is not the only configuration of OTA. I can have this structure, which is also an OTA. The difference between this and this is the action here is in the NMOS devices here versus PMOS devices over here. There are other structures which are multiple stage devices. There's this structure here, this structure here, this structure here, and so on and so forth. And so what you can see is that when you look at all of these things, there's really a wide range of structures that are all recognized by an expert human designer as OTAs. But for a tool to be able to recognize this is not so simple. And this is where we can leverage machine learning in order to handle this, because machine learning can recognize variants of a particular structure. So if you recognize features, for example, those features can be composed, and then you can recognize that a particular block is an OTA, for instance. So when we go back to this picture over here, we had this netlist, which was at the transistor level. I've shown this as a block here, but it's actually a transistor level description. The idea is to ask the question, as I'm going through this hierarchy, within this entire structure, which group of transistors corresponds to the OTA? And of course, it's not just the OTA. If I have other types of blocks, such as VCOs, LNAs, etc., I might want to do exactly the same. So we have two approaches for auto-annotating these netlists. The first one is, as I said, using machine learning to identify commonly encountered topologies, such as OTAs or LNAs or VCOs, etc. And the idea here is that these are all variations of some core structure. The core structure is in the form of a netlist. So unlike an image, you actually have to deal with graph-like connections over here. So you have transistors and nets that are connected in the form of a graph. So if I have this structure over here, I can take the entire structure and represent it in the form of a graph. And if I want to pull out this hierarchy, the question I want to ask is a classification question. If I take a specific node over here, does this belong on the inside of the OTA or not? So since this is a graph, we can train a graph convolutional neural network to handle this. And based on that, I'll skip over the details. We can say that these brown nodes over here are actually nodes that fall inside the OTA. And so we've then reconstructed the structure of the OTA. We now say that these blocks can be pulled in over here, and the remaining blocks are something else, and we'll use other techniques to identify them. In this case, they're actually pretty simple because they're switches and capacitors, so they're really primitives already. But over here, when you identify the OTA, you want to go to lower levels of hierarchy, such as differential pairs, current mirrors, etc. We can do this for more complicated structures too. For the phased array structure, for which we have the recognition of low noise amplifiers, mixers, oscillators, bandpass filters, buffers, inverters, etc. And this is the confusion matrix, which shows you that everything is perfectly recognized. The actual matches the predicted. So all the 78 nodes that correspond to the LNA are predicted correctly, and so on. Now, this approach works well. The problem with it is that it requires a lot of data entry. And what that means is that you need to provide you need to train your engine in order to be able to recognize OTAs and LNAs and mixers and so on. So you need to provide training sets. Harvesting those training sets is a very manually intensive process. And also training requires a certain amount of effort. So we have a second approach that we also use, which is the notion that you want to identify array structures in a layout. In an analog layout, whenever you have structures that are repeated, typically the requirement is that they have to be laid out in a symmetric way. Array structures are often put together using symmetry, matching, or common centroid structures, so you can design them once and then replicate them. So for instance, over here, you can see a flash ADC, and in this case, you can see a comparator and a resistor, and this thing is replicated many times, and you would want to maintain some kind of matching between these. The resistors should be similar, etc. If you look at this is an ADC structure, you can see again there's a capacitive array, which is a binary weighted array that's shown over here. In some cases, the matching is not exact. In some cases, it's approximate, but you still need to match. So for instance, you have a common gate low noise amplifier here, a common source low noise amplifier here. This is certainly not identical to this because you can see that the gate of this transistor is connected to V bias and V in. Here it's connected to V bias and a capacitor, but they're pretty close. So in this case, we use the notion of a graph edit distance. So if we say, well, if I edited the graph corresponding to these, how many changes would I need to make to match the left structure to the right structure? And if I do that, then if the graph edit distance is sufficiently small, then I can say they're close and I should match them. And we can use a neural network to find the graph edit distance. Notice that the difference between the left side and the right side is that on the right side, I don't need to train it on specific structures such as OTAs or LNAs, etc. I'm just looking for symmetry or approximate symmetry. So that makes it a little more general. So these are some structures that we've taken from auto annotation to layout just to show you. So in this case, you have an R2R structure. That array is recognized, and then you take the switches and the OTA, and that gives you the overall DAC. In this case, we have an FIR equalizer. This is kind of tricky because what's required is that all of these taps over here, there are 10 taps, 3 of them are shown here. They have to be laid out symmetrically with respect to R1 and R2. Moreover, what's tricky is that these current sources actually are different. Some of them are 5-bit sources, some of them are 7-bit sources. So this is where approximate matching comes into play. And the eventual layout looks something like this. You have R1 and R2 here. The 10 taps are shown here. The larger current sources are taps 0, 1, 2, 3, and those are symmetrically laid out about R1, R2. And the other taps are also symmetrically laid out. So the key to all of this is the auto annotation step, which recognizes the individual building blocks and creates the overall structure. So once we have this, we kind of jumped through some of the processes over here. Our goal here was really to identify these blocks, and we showed the eventual result. But how do you get to this? We first need to create layouts for the individual structures. So we'll first look at creating layouts for the lowest level structures or primitives. In order to do this, we need to first abstract the process design kit. The design rule manual typically is really complicated. It's human readable. It's written in plain English for the most part. And that has to somehow be abstracted into something that's simpler. So what we try to do over here is that we work with a grid-based structure. But unlike the conventional lambda-based grid, we do a few things that are different. The first thing is that the grids are layer specific. So the grid that I use for metal 1 won't be the same as the one that I use for poly or metal 9, etc. The second is that I also have major grid lines, which are the solid lines, and minor grid lines. And the idea is that the wires have to be routed along the major grid lines, but they can stop on the minor grid lines. And in fact, this turns out to be pretty effective in capturing a wide array of design technology nodes, and we've applied this to a number of nodes. Some of the design rules require Boolean rules, as mentioned earlier. So in this case, a diagonal via is disallowed, even though it might maintain the spacing requirement, and so we can capture those in that way. Okay. So now, once we have this, the idea is that if I look at some of these structures over here, these are various types of OTAs and comparators. Each of them is composed of this same building block, which in this case is the differential pair. So that's a primitive structure that's widely used. So we have a parameterized way of generating layout for these primitive blocks. What this means is that if I use a different number of fins or fingers or a W by Ls, then I can automatically generate this in a parameterized way. And then the idea is to take all of these at the lowest level of hierarchy and then perform block assembly to get the overall layout. So this kind of shows you what we end up doing. So in this case, you have a situation where some cells may require a body contact, some may not. So we have ways of parameterizing the cell to have a body flag or not. We can change the aspect ratio. This is a poly resistor that you can see. It can be built with this aspect ratio or this. This flexibility is really important for getting compact placements and low parasitics. Similarly, for capacitive arrays, we can change the dimension of the array, the number of sub-building blocks in the array. We can use multiple parallel wires. This turns out to be really important in FinFET technologies because wires are very resistive. So if we use multiple parallel wires, we effectively reduce the resistance of the array structure. We can change the layout pattern. I talked about this earlier. It can be common centroid or interdigitated, depending on which is better for the structure. We can change the active gate length, the width, etc. And so there's a wide range of structures that we can use. This gives you kind of a list of primitives that we are currently working with. These actually cover a large number of potential building blocks. We also have a way for users to specify their own primitives in case there's something that appears frequently in their designs, and these cell layouts can be parameterized. So once you have these basic building blocks, now you need to perform block assembly, which is placement, floor planning, and routing. And over here, if we look at this, for example, we have the switch capacitor filter, which consists of capacitor primitives. The OTA consists of all of these primitives, etc. So what we can do is build this solution bottom up. So we first build a placement for this structure, then we combine this to a placement for this structure, then we combine this to a placement for this structure, and the placement is inherently performed bottom up. Currently, we use a simulated annealing-based engine because the number of blocks at every level is relatively small. In some cases, our blocks may require a guard ring, which is a noise prevention methodology. So if the block is noise sensitive, we can actually incorporate that as well into the layout before block assembly. For routing, we actually go the other way. Remember that we go bottom up for placement. For routing, we go the other way because all of these structures are built on a grid. So when I take two of these and put them next to each other, they may not align as well onto a grid. So for routing, in order to maintain the grid relationship, we actually go top down. We first route at the topmost level, then to the next level, and then to the last level. And this allows us to meet our requirements without incurring design rule errors. We also incorporate power routing. Power routing is really important because analog circuits often feature very large currents, and these are DC currents that flow constantly. Unlike a digital circuit where your current really is fed to the circuit at the time of switching, in an analog circuit, if you have a current bias, for example, it can be constantly sinking current, which induces IR drop in the power grid. So we need to design these very carefully and make sure that the IR drop is not large so that the quality of VDD and ground is very high. For detailed routing, again, without going into a lot of details, we use A-star search. We perform routing on a grid. The important thing here is that in both placement and routing, we need to honor these requirements, such as symmetry, matching, maximum length. For routing, we may have to shield some wires to make them more noise immune. And of course, there are kind of requirements on FinFET design rules also that need to be taken into account. We consider parallel routes in multiple ways. So I've shown parallel routes within a primitive as shown here, but we can also have parallel routes across primitives, across hierarchical blocks, which reduces resistance, which is particularly important. So in this case, you have kind of multiple redundant wires for power routing. Here you have multiple redundant wires for signal routing. They're not redundant really, they're actually used to reduce resistance. So redundant is a little misleading over here. We have two detailed routers. There's one detailed router which is based on this structure, and it works very well for designs that are not very congested. For designs that are very congested, there's an analog detailed router that has been put together by our colleagues at Intel. And it's a SAT-based router, and it provides correct by construction design rule solutions. It captures the constraints in a satisfiability-based formulation. And so when you have scenarios where you have pre-routes that are specified by the designer and you have very tight routing specifications, this router actually works really well. And in fact, it can capture these Boolean design rules very naturally because it's a SAT-based structure. Now, one of the things that I have not talked about yet is the fact that when you perform this placement, we need to meet performance constraints as well. So far, I talked about symmetry constraints and so on. How do you handle performance constraints? Really, these translate into limits on the parasitics that you're willing to encounter. We've looked at several techniques for doing this using machine learning. I'll talk about one such technique over here. So in this case, for example, if you didn't do anything that was kind of performance conscious, your schematic might have a performance that's something like this, but when you look at the post layout performance, it actually degrades, and in some cases it can degrade quite significantly. Here, the unity gain frequency of this telescopic OTA goes down by quite a significant amount. So what we try to do through this process is that we take the analog IC placement and we use graph neural network techniques to predict whether the performance is good enough or not. So recall that we are doing this within a simulated annealing engine. So if we can have a fast predictor, which is inference on a graph neural network, which can be very fast, when we get a candidate placement, we can ask the question, does this meet specs or not? Or what is the probability that this will meet specs, etc. So if we have a predictor of this sort, that can come about using a trained graph neural network. One such approach is something that was published it was led by my colleagues at Texas A&M University. So it's basically a graph attention network, but unlike conventional graph attention networks where the attention is based on the nodes, here the attention is based on the edges of the graph. And so using this approach, using some kind of a pooling approach with edge attention, we were able to use techniques that predict performance. Now, the advantage of using this kind of a structure is that, as you can see, going from left to right, the edges are being collapsed. So if you have structures that are fundamentally very similar, but not identical, like those variations of OTAs that I talked about earlier, at the initial stages, they may look different, but at the final stages, they may look very similar. So it's relatively efficient to capture performance using these. So the way that this gets kind of fitted into the overall solution is that the simulated annealing objective is weighted sum of area, wire length, and this thing that comes from the P network, the neural network, which is basically a weighted sum of the probabilities of meeting some specific performance constraint. And this probability is estimated using the graph neural network. To give you an idea of how this performs, these are 3 different types of OTAs. And if you look at the manual design is always the best performance. So we will not typically do better than manual design. In some cases, we actually do, but in this case, we don't. And that's okay, because if you can come to being very close to manual design and at the same time you can do it with a much faster turnaround time, there's still value to that. If you look at the conventional approach, which is automated placement without considering performance, that's the purple bar. And in many cases, there's a significant degradation over here. If you look at a network which is self-sustainable or trained specifically for this, so you train it for Cascode OTA and you apply it on a Cascode OTA. This is a CNN-based approach that was previously published. This is our approach. You can see that it doesn't quite do as well as manual layout, but it certainly does better than the purple bar over here. P in general does a little better than the CNN. But what's really interesting is that you can perform transfer learning here. So for example, you can take something that was trained on Cascode and then perform transfer learning to apply it to the current mirror or the 5T OTA, which is much more rapid training. And with transfer learning, you can actually do kind of about as well as the network that was trained specifically. In some cases, you can actually do even a little better, but that's an accident of inference. But generally, you can get very close to the green bar over here, whereas for the CNN, that's not often not possible. Now, because we're doing this as an open source project, it's really important for us to also pay attention to the software architecture. So like I said earlier, this was a distributed team, one in Portland, Oregon at Intel Labs, one in College Station, Texas at Texas A&M, and one in Minneapolis, Minnesota at the University of Minnesota. So initially, the way we did this was we divided the flow into multiple stages. Each had a primary owner. And for example, the place and route work was mostly done at Texas A&M. The early part was done mostly at the University of Minnesota. And then the analog detailed router was mostly done at Intel. And then we used kind of a loose Python environment to couple these together. We used Docker containers so that we could quickly bring up these build environments and so on. More recently, we've updated this to have a Python interface all through. So currently, we have basically a structure which allows all of these modules to communicate through Python interfaces. And so it actually makes it much easier to plug and play new versions of any of these. Beyond this, we've also used a number of software tools. This has been kind of a very educating experience for especially all of us at the university. And we've used GitHub for source control and communication, which I think is pretty standard nowadays. But in addition, we've also been integrating unit tests and integration tests. We use continuous integration using Circle CI, etc. And so all of this really helps us to work well in a distributed software development environment. The other thing that we've also done is our original goal was to allow a complete amateur to provide a netlist over here and then produce a GDS over here. But as we were working with Intel, it turned out that there was a requirement for other forms of using this engine too. So for example, an expert designer has things that they particularly want, and our annotation may not actually catch that. So the expert designer might want more control. And as you can imagine, at Intel, there are quite a lot of expert designers. So we modified the flow to have multiple entry points. Now, because all of these were built modularly, that was easy to do. The first one is no human in the loop. You send in this netlist, click a button, and you get the output. The second one was a situation where the user provides constraints over here. The third one was even more control, where the user provides constraints as well as specific place and route guidance. So they might provide pre-placed routes, or they might say that these routes should go roughly along this global guide, etc. And the fourth one, which gives kind of much more control, is that the user codifies placement and routing in Python. And this is particularly useful when you want to build very large array structures. For example, for very large transistors in power delivery circuits, the designer knows more or less what they want to do, but they don't actually want to sit down and figure out where every transistor goes, what the self-heating rules are going to be, etc. So I'll show you some use cases from our colleagues at Intel. These were done by designers at Intel. There's an analog LDO and a digital LDO. That's a low dropout regulator. And in this case, the green blocks were built using Align. The white blocks were manually designed. And so you can see that the die photo looks something like this. And the interesting thing is that the mask design, or the backend layout which Align performs, was kind of significantly faster. If this was done manually, then it took about 96 hours. If you looked at entry point 1, which was no human in the loop, it was 96x faster. If the user provided constraints, then it became a little slower, and I'll show you the quality in a few minutes. And if the user provided constraints as well as some place and route guidance, there were two versions of this that we tried. They took about 8 hours or so, but each of these was significantly faster than the 96 hours that it took here. So this shows you the results over here. This is the manual design over here. It's the most compact. This is entry point 1, which requires no human in the loop. Entry point 2 has the user provide constraints such as symmetry, etc. Entry point 3 has the user provide place and route guidance. So you can see that progressively, as there's more guidance, the layout becomes more compact. But as it turns out, for the original specifications that were provided to us, even entry point 1 met all the constraints. In fact, in analog circuits, typically, because they are a small part of the overall area, compactness or area is not a primary consideration. It only matters because larger area typically leads to larger parasitics. But in terms of the overall chip, it's typically not a huge issue. So that gives an overall view of what we've done in Align so far. It's a continuing project. We continue to work on it. The GitHub repo is shown over here. We have, this is a slightly older screenshot, but fundamentally, we've made updates to this. We've made a couple of releases so far. This is the README. Hopefully, it's something that can be kind of looked at. This is a gallery of some circuits that we've designed using Align. And you can see that the colors over here signify the classes of circuits. So these red ones are low-frequency analog circuits. The green one here is wireless. The blue ones are wireline circuits. The brown ones are power delivery circuits. So this concludes the talk. I hope I've been able to give you a good overview of the project. And I'd like to thank all of my colleagues and collaborators who've really done the bulk of the work on this project. Thank you.
Thank you, Professor Sachin. We have several questions. Let me start with the first one from Ian Ray. He's from ST Microelectronics in India. So he's asking, unannotated netlist means like Verilog netlist, just connection between components?
It's a SPICE netlist. So it's a transistor level. It specifies transistors, parasitics. It can be hierarchical, so you can have sub-block specifications, etc.
I see. Okay, so it's SPICE. Another question from the same person. Do we need to decide the level block at which we need to ask the tool to identify structures?
No, all of that is done automatically. So the recognition process actually goes hierarchically. It goes to kind of higher level blocks and then identifies sub-blocks of those blocks. So all of that is done automatically.
Oh, amazing. Another question from Ian. Is there any automated way to get the abstract PDK view? Since the original one are in rule decks like Calibre or PVS format, etc. So
yeah, currently we are doing that as a manual process. The justification for that is that it has to be done once for each technology node. So it is a certain amount of effort, but we're doing it manually. We are not automating that at the moment.
I see. I got now some questions from Professor Sergio Bampi from Works, Porto Alegre, Brazil. So on slide 16, could you leverage better automatic layout results if you have the block level hierarchically built layout with human aided annotated by the designer of the blocks, like OTA blocks, like matched resistor pairs? I mean, to take less ambiguity from the automatic way you describe it.
Hi, Sergio. Hope things are going well. Thanks for your question. So in this case, we are looking at what I call the no human in the loop flow later on. So in this case, we are trying to extract everything automatically. In fact, what we do over here is if the designer provides some hierarchy, we even destroy that because different designers may try to view hierarchy in different ways. And we want to choose the hierarchy that works kind of best for our tool. However, later on, near the end of the presentation, I talked about the idea that we could have multiple entry points. So for example, for entry point number 2, the user could specify that they want a specific type of hierarchy that they would like to have followed. And in fact, our designers at Intel typically do provide these types of hierarchies. And in that case, if they specify a constraint, then we honor that constraint.
Okay, thank you, Professor. So now I have several questions from Patrick Mendes. He's from Cefet in Belo Horizonte, Minas Gerais, in Brazil. There are, let's see. Okay, Professor Bumpy is saying thank you for you, Professor Sachin. So hope to see you soon. So coming back to the question from Patrick. There are several ways of using common centroid structures. Can the primitives be customized? For instance, one can choose how many parts will the diff pair be split into. Or are they fixed ones? Just some types and sizes are available.
Yeah, so that's a great question. So currently, like I said, this is a project that is in progress. So in fact, that is an area that we are actively working on for both transistor and capacitor arrays. We are trying to improve the quality and flexibility of common centroid placement. So currently, there is a version that is somewhat limited, but in the near future, we expect to have much more flexibility that captures the issues that you pointed out.
Nice. Another question. Are the capacitors, resistors customizable depending on the tech node, if poly 2, min, or highest are available or not? The primitives are based in which materials?
Yeah. So like I said, we have kind of some default primitives that are provided with Align, but the idea is that we also intend to have the designer be able to provide their own primitives. So for instance, if you want to use a different structure, whether it's for a passive or an active device, then we plan to make this make it possible for the designer to specify that. So you'll notice that my response is mostly in the future tense, that we plan to do this, etc. Currently, we can actually do it, but it requires significant kind of input from the developers to facilitate that. We are hoping to make that easier for the users in the future.
I see. Nice. So you have a very good, this idea of customer and how you are developing. So you are thinking on both ways. So you need to make that easy for the customer as well.
Yes.
the way user likes it. That's very good.
Yeah. So the background to this also is that the way that this was originally, so all of this depends on funding. So the original charter from DARPA for our project was that we should have entry point number 1. And that's the reason why our original attitude was to make it completely automated. But as we went through the project, we found that there was value to these other entry points as well. And that's why we're enhancing the flow to enable that.
Mm-hmm. Yeah, no, that is very nice. Another question from Patrick. How about the guard rings? Are they included in the customization in the primitives with and without them?
Yes, exactly. That's exactly what we do. And then it's not just about the primitives. You can actually have a guard ring around a larger block. So you can have, for example, if you have an OTA, you can put a guard ring around that if needed.
I see. Last question from Patrick. From the netlist, it's not possible to know if the circuit is a current or voltage mode. Do a line can receive specs from CM circuits and prepare the layout for proper thermal constraints addressing?
So in principle, yes. In practice, I think the way that we handle thermal constraints right now is not through any kind of thermal simulation of any sort, but in terms of some kinds of layout rules. So at this point, a line is not sophisticated enough to handle general thermal constraints.
I see.
It requires human input.
Okay, yeah, you need some human input. So some questions from Visir Nikhil from Blue Spec in Boston, Massachusetts. So the pure bottom-up hierarchical placement may waste space, may it not? The pure bottom-up hierarchical placement.
Yeah. So hi, Nikhil. Good to hear from you. So you're right that it may not be the most space efficient. Now, the interesting thing here is that in analog layout, typically area is not the biggest constraint. In fact, there are many scenarios where if you look at this picture, for instance, you can see that there's a lot of white space or black space over here. And this is enforced by the fact that you have symmetry requirements which require, let me get rid of this, which require these blocks to be symmetrically placed, etc. So when you look at die photos of analog blocks, typically area is not the biggest constraint. The reason why area matters is because a larger area means larger parasitics. But block packing is less of an issue than it is in digital circuits. So, so far we found that these approaches seem to meet the designer constraints. So they seem to be good enough and they seem to be consistent with the way people do design.
Nice. Another question from Nikhil. Are there any thermal considerations during place and route?
So we incorporate, this is similar to the question that was asked earlier. We incorporate them in terms of things like spacing requirements and so on. We actually worry a lot about reliability issues, which are somewhat related to thermal issues as well. So if you have, for example, a wire that carries too much current and could be an electromigration hazard, and that's particularly important in analog circuits that carry steady DC currents, then we handle those.
I see, nice. Yeah, you are the electromigration guy, so I'm pretty sure you want to let those pass. That's nice. So another two questions from Sai Sharan. He's from Vardhaman, Xiaoji, India. The first question is, how reliable is this automatic flow in terms of DRC and LVS?
So not all of our layouts are completely DRC clean, but at least for kind of familiar structures, they are DRC clean or they have a very small number of DRC errors at this point. LVS is generally clean.
Yeah, I think, LVS you must need to be like most clean to make it. How much computation power is required to run this flow since there are many ANNs use it?
The neural network part, really the effort comes in training the networks. And we've done those on standard CPUs, GPUs, etc. once you've trained the neural network, the rest of it can be run on a regular desktop machine.
Oh, nice. It's not so powerful. Another question from Mishi Stockinger. He's from NXP here from Austin. How does this tool take into account guard ring and spacing requirements for latch up? For example, if there is an external I/O pin connection to the analog block.
So currently, if there are scenarios such as that, I think it would probably be more useful for the designer to provide these constraints through entry point number 2. So we can actually hybridize this, where we generate some constraints from here, and we also honor user-provided constraints. So we are still in the process of developing our engine. We are actually thinking very actively about the kind of issue that you've talked about over here. For example, another scenario is if you have an RF circuit where you have an external antenna and you need to perform some kind of route matching, then how do you kind of have the circuit layout interact with the IOs? We don't have a complete solution to that right now, but it's something that we are working on actively.
Nice, thank you. Now a question from Federico Passerini. He is from Infineon Technologies in Austria. Do you know the approach of Magical, University of Texas? Yeah. In case, can you please quickly compare it to Align?
Yeah, so Magical and Align are both funded under the same DARPA program. So we are very familiar with each other's approaches. Magical is generally a smaller effort than ours. So for instance, they don't target as wide a range of circuits as we do. We've also been working very closely with industry designers. So I think we have more of a kind of a groundedness in that part over there. But having said that, the work that's being done by Magical is complementary to this. It's very good work. They're an excellent team of researchers.
Nice. A question from Panumas Kumsat. Does it take into account the interferences between various metal paths?
I think you're talking about crosstalk and so on. So I think those kinds of constraints would come about when you're considering shielding requirements of some sort. So those kinds of requirements would be captured by shielding constraints.
Nice. Another question from Professor Sergio Bumpy. How have you standardized the pragmas, like in HLS annotation of HLL, C++ code, can be written by the human interventions in phase 1, 2, 3? This is slide 51.
Yeah. So by and large, all the interfaces, if I understand you correctly, all the interfaces are written in terms of JSON files. So they are kind of relatively easily human readable, but at the same time, they're machine readable. They're fed. We've created our own kind of pseudo standard interface between these blocks. I'm not sure if this is exactly the question that you are asking.
Yeah, Professor Bumpy can tell better.
Yeah.
Yeah. So how many people are in this project? This is just a side question. So
yeah, it's about 15 at the moment.
Okay.
And it's actually unbalanced because some of them, for example, Steve Burns at Intel is a very, very experienced industry researcher. There are a couple of other really experienced researchers at Intel. We have a few postdocs and a lot of students. So everyone's kind of contributing in unique ways.
Yeah, it's because it's a great project, and there is a lot of things you guys are doing. And I think like how you can centralize everything, like you are showing, like you have GitHub and those things to get all your code in sync. But it's still like when you put like all of these people together and working, I think it's a big work to do. And have everything like
it's a very good team, and they're very nice people to work with. So it's been a very enjoyable experience.
I believe so. Let me see another questions. So many people saying like, what a great talk. It's amazing talk. So Sai Sharan also is saying it's a great talk. Professor Ricardo Reis, how flexible is the tool to handle different transistor, resistor, and capacitor sizes?
It's pretty flexible, and that's part of the primitive layout generation. So for instance, if you change, if you have, a current mirror and you change the sizes of your transistors or the ratios for the current mirrors, then we can generate those layouts automatically.
Okay. So Professor Sergio is coming back. So pragmas are like a standard way to annotate the designer's intent into the high-level language code for high-level synthesis. This needs to be standardized by the align tool. Okay.
Yeah. So that's if all these constraints, for example, that are also provided. They're actually currently provided using a JSON format, but we are creating more designer-friendly language where the designer can just say, okay, create symmetry between block A and block B. So we're creating a simpler language for that.
Okay, so you have the JSON just to document everything, and then you are creating a friendly interface to the user.
Yeah.
Nice. Patrick, is the tool open? How can we test it? I think you showed the link for the GitHub, right?
This is the link down here.
Yeah. So Patrick, you can get the code there. So the GitHub. I think that was the last question. So any more questions? I know like a bunch of questions. This is a very, very interesting topic. Thank you, Professor Sachin, for the great topic. I have only one last question. How easy or difficult you think this is going to be like for 5 nanometer, 3 nanometer, 2 nanometer, like to be like in analog? Are you working with digital? So I just want to understand like for the analog, how is that?
So we've applied it quite actively to a 12 nanometer technology, which is FinFET. Again, I think things become more complex as you go to lower technology nodes. We don't have access to all of these, but with our collaborators at Intel are applying this to newer technology nodes within Intel as well.
I see. Is if you compare like analog with digital, is the analog a little bit simpler than the digital, or you think it's like the same thing? Like you need to obey like a bunch of those rules and.
It's smaller than digital, but it's a lot more complicated, and that's the reason is because the constraints are more complicated, and that's why the expert human designer has been so important all this time. So what we are trying to do is to try and improve productivity while keeping the quality the same.
Yeah, this is amazing work. Okay, the final call for questions. Any more questions, guys? Yeah, Professor Sergio Bump is saying it's a great talk. Looking forward to teach using Align tools.
Thank you.
Okay, another question from Pranumas. Should an analog layout engineer find a new job? Anything left for them?
I think like anything else, the task becomes a little different. I think an analog layout engineer can also become more productive with a tool such as this. So if you look at, for instance, the multiple entry points, we've seen that in general, the quality of this one, which requires intensive interaction with the layout engineer, is more compact than this one over here. So I think it's a different type of expertise that's required. And I mean, certainly it's my hope that we'll get to the point where we are as good as the layout engineer and we keep pushing to be better and better. But like anything else, things evolve and we just have to develop new skills as new technologies come forward.
Yes, I agree. It was a good question. So if no more questions, I think we can close the session. I want to thank you, Professor Sachin. It was a great talk. It's a very interesting and hot topic. I think it's amazing. Everybody was very interested in your talk. So thank you so much.
Thank you. It's my pleasure to be here.